Hello. Hello. Let us start our discussion. I hope you will join soon. We have discussed, so far we have gone through two modules. One is the strain analysis, another is stress analysis. What is the specialty of our discussion is, in our strength of material, we have discussed the stress condition and strain condition with the idea that the strain is being applied, say, at the end of a prismatic plant, say, longitudinal direction, maybe tensile or compressive, whatever it may be. Now, what will happen? The stress across the cross section, we have defined that it is a resisting force per unit area of the cross section itself. It is the resisting force per unit area across the cross section itself. Now, we have discussed the strain as the deflection per unit length of the system itself. But what we have considered, for a particular cross section, the stress or this resisting force is same and uniform throughout this length. Similarly, we have understood, we have taken into these assumptions that for a particular cross section, the strain is same and total cross section is getting the deformation, either elongating or contracting itself. We have generally decided that the stress is uniform and equal throughout the length of the cross section. What is the set size of the cross section and what is the external load? This is a common corollary, you can say, common assumption we have taken, and we discussed based on this assumption with so many theories and everything. But actually, in course of time, what we have observed, that this is a wrong decision, a wrong conception that the stress or the resisting force per unit area is uniform across all points of the cross section itself. You see, hello? Hello?
Yes, sir.
Do you listen to me? Hello?
Yes, sir.
Is this page is very visible? Hello? Is
Yes, sir.
this matter is visible? Hello? Please answer. Hello? Hello? Is this matter is visible to you? Amit, do you listen to me? Amit, Kundan,
Yes, sir.
this present case is visible to you.
Yes, sir.
Yesterday, I've gone through this idea also, but the page was not visible to me, you, because in my record I find nothing is there. You should inform me that you are not listening anything. Okay, I'm continuing. So I'm repeating the same thing.
Okay, sir.
Okay. And listen, tomorrow first period, I will take another additional class to back up this lossy loss from my side. In the first period, I will give the information separately.
Okay, sir.
Okay. But in our idea, what we have found in our practical process is that this idea, the stress is uniform throughout a cross section is wrong, and that's why the strain, constant strain, is uniform throughout the cross section. That's also wrong. That can also vary across the section itself. Stress can vary across the section itself because loads per unit area or resting force created may not be the same in throughout the area itself. Somewhere it is the maximum and somewhere it is the minimum. And the value of the maximum stress may be much higher than the average stress itself. So if you can design and according to the average stress, your design will be wrong because you are supposed to carry your stresses or your work or your beam to much higher, to be resistive to much higher load. So your design will be wrong. That's why now we are going through the stresses at the point of across any cross section or any body, and the state of strain which is developed due to the stress itself. Now, how will you do? Question is like this. The strain components now related to displacement, whatever be the displacement per unit length is the stress, is the definition of strain. So it may be average and maybe point, but the definition remains same. Now, here we are supposed to follow 6 Cauchy's strain displacement relations. We will follow again the Cauchy's stress relations. Here we will discuss the relation between stress and strain in terms of the equations. It is defined as constitutive equation itself. This term constitutive has a specific meaning. Just 1 second. This term constitutive may have certain specific meaning. Actually, these equations are, which thus defined, are based on a practical data in which the material resists the deformation itself. And the consecutive relations are mathematical consecutive equations are mathematical disciplines of the physical phenomenon based on the experiment observation and established principles. So what do you mean by classification? It just gives you mathematical statements about what we have gone through in the theory, about the physical deformation which takes place due to the action of various types of external forces, various magnitude, they may act together, they may act differently, etc. But and these equations will give you a mathematical deformation or mathematical statement of this physical phenomenon of stress and strain. And this stress and strain, the phenomena are based on experimental observations. And with the basis of this experimental observation, these equations are made. They are also an approximation. It is also this all these equations also an approximation of the two behavioral patterns. Since an accurate mathematical representation of the physical behavior is extremely difficult and complicated. So we never went to do the same because whatever may be the practical problem, we have to use all these equations and to know our stress and strain condition in our practice. And in our practical application of this equation, we find that these are accurate. These are more or less adequate to give you the established, give you the result itself. So we did not never we go for the accurate statement of equation because it will take me much more time and energy and you will not gain much of it because more or less you get the same result by approximation. Okay, now this consecutive equation despite being the behavior of a material, but not the behavior of a particular body itself. Therefore, the equation relates the state of stress of the point to the stress of strain of a point. So, what we are saying? That is the how that particular material behaves. And this behavior can be given to us only the equation relates the state of stress at a point and state of strain at a point. And this relation is being given by the constitutive equation itself. Okay. What is the general statement of Hooke's law? We know it very well. There is a uniform cylindrical rod of, say, some certain diameter known to us, subjective to tensile force, say, it can be compressive, all right. As it is known that the experiment of them is postulated in the elementary strength of material that existing axial force sigma is directly proportional to the axial strength epsilon up to a certain limit known as proportional limit or elastic limit. Hence, stress is proportional to strain. Well, so long the stress or resulting the load resulting the stress is within the elastic limit itself. And you know what is the elastic limit very well, and what is proportional limit. They're more or less same for the capital material. They're more or less same. There, the stress or there the load, which when removed, will the concerned body will go back to the original shape and size. That is the elastic limit. So everything is applicable only when it is within elastic limit itself. And so many things which are done in our strength of materials, all applicable only when the concerned load and concerned I mean the beam members or etc. will be acts within their itself, elastic limit itself. Now, we know there is a constant of proportionality that is of the proportional limit. That is constant of proportionality because there stress is proportional to strain. So we have the constant of proportionality that is Young's modulus E. Thus, sigma is equal to epsilon into E. Next, there is another phenomenon we can very much remember: the lateral change in lateral dimensions. When the uniform block elongates, the lateral dimensions or the lateral diameter decreases. When diameter length in longitudinal length increases, that diameter in the lateral side and the lateral dimension it decreases. And the elementary set of material what is taught, the ratio of lateral strain to lateral strain to longitudinal strain is defined is a constant, a fixed ratio. Also, it is also achieved practically, it is defined as Poisson's ratio. So, we have the knowledge of stress is proportional to strain and lateral strain is proportional to longitudinal strain. These two relations, this is the what we say, the relation between stress and strain, and this relation is in this relation of this knowledge is related to 6 rectangular components of stress. 6 rectangular components of stress to 6 rectangular components of strain. So what we are getting here, we want to relate 6 rectangular components of stress to 6 rectangular components of strain. Okay, or opposite, 6 rectangular components of strain to 6 rectangular components of stress. And we'll assume each of these 6 independent components of stress may be expressed as a linear function of the 6 components of strain and vice versa. That is, each of these 6 independent components of stress may be expressed as a linear function of the 6 components of strain and vice versa. Okay. This stress is proportional to strain is applicable here, but here we are saying representing the strain by means of 6 independent components of equation and stress by equal amount 6 rectangular function, and they are equating to each other and vice versa. Thus, what will be the strain? Mathematical expression. This is given by again Cauchy's analysis. Strain or sigma just a minute. Now, these are the 6 rectangular stresses. This is sigma x, sigma y, sigma z, and tau xy, tau yz, tau zx. These are the tensile stress along x, y, and z direction in 3 mutually perpendicular rectangular coordinate system. And tau xy, the shear stress you know, is shear stress along xy plane pointing towards the positive direction of y-axis. Tau yz, that is that on yz plane, and zx, that zx plane. It is given as A11 EXX, A12 EYY, A13 EZZ, and A14 gamma XZ, and A15 gamma YZ, and A16 gamma ZX itself. All these 6 stresses you see, 6 stresses are function of strain along x direction, y direction, z direction, and shear strain in xy plane, yz plane, and zx plane, multiplied by so many constants, which A11, 12, 13, etc. Same is the case sigma y, sigma z, and tau. Same is the case. Here only all are same. Only these equations are only the constant are different. This is starting from. It is coming from. All these reactions are same. The other is same. The are same. But 1, 1, 2, 1, 3, 1. Next comes 4, 1, 5, 1, 5, 6, 2, 6, 2. Or here is 1, 2, 2, 2, 3, 2, 4, 2, etc. Then comes all 6. Here this is the 6, 1, 6, 2, 6, 4, 6, etc. 2, 6, 6. This is the constant. We constant the Cauchy's constant. This is we are supposed to know. If we are to know all these stresses at a particular point, which are in rectangular coordinate axis itself. Conversely, it is exactly opposite also possible. If we can write the same equation like this, f psi axis is given by E11 sigma x, sigma y, sigma z, tau xy, tau z, tau c. Then tensile stress x-axis, tensile y-axis, tensile z, shear stress xy, shear stress yz, and shear stress zx. F psi always same process will follow. Both this equation is valid. Equation number 3 is a multiple equation. Number 2 is a multiple number of equations. And 6 equations. Same is the case. Equation number 3 is also 6 equations, where A1, A2, A3, B1, B2, etc. are all constant for a given material itself, with a particular part, etc. If we solve equation 2 as 6 simultaneous equation, one can get equation 3 and vice versa itself. So you have to solve this thing. If you solve with this all these terms, or if you solve this, you get all these x. So if you know sigma is sigma y everything, and if you know all this constant, you can simply calculate the strain or reversely stress. Now, for homogeneous linearly elastic material, 2 and 3 are known as generalized Hooke's law. It is not the Hooke's itself that says the proportional to strength, but it's called strength, although it is generalized Hooke's law. Actually, this is done by Mr. Cauchy's himself. And here we have 36 constants are currently involved here. Mr. Cauchy is making this equations on the basis of Hooke's law, and it is generally defined as the original from Hooke's law. Hooke's law is defined as Hooke's law itself, generally Hooke's law itself. Now let us go through the stress-strain relationship for an isotropic material itself. Hello, am I audible? Hello?
Yes, sir. Yes,
am I
sir.
audible? Students,
Yes, sir.
listen me. Is nobody is there? Very bad. We can now make a further assumptions that stress-strain relation for an isotropic material itself. We can make a further assumptions that the ideal material we are dealing with has same properties in all directions so far as the stress-strain relations are concerned. So there are two things we have to know now, define what is isotropic material. Isotropic relation is defined as a material which has at a particular point have the same properties in all directions, x, y, z, etc. They have the same properties, but they in point to point their property may vary. But for a particular point, they have the strain properties so far as stress and strain relations are concerned. Means for a particular point, their stress or strain is same in all directions. This means the materials are not dealing with, or we are dealing with isotropic. It don't have a directional properties. It is don't have a additional stress or any reaction according to any particular direction. It is same everywhere. It don't have any additional stress anywhere else. We must distinguish the assumption of isotropy, which is a particular statement regarding the stress relationship given at a point, and that of homogeneity, which is a statement that stress-strain property, whatever they are, the same at all points. Here, the stress-strain property was same for a particular point in all directions, but for a homogeneity, the stress-strain property of a homogeneous material is same everywhere. They are same at all points. Say for rectangular timber of a timber bar of rectangular grain is homogeneous but not isotropic. They have same property everywhere, but they don't have a particular or a property or a particular property of same everywhere, same direction in all directions. But throughout the portrait, throughout this volume, it is same. But in any direction, it may not be same. So it is homogeneous but not isotropic. Now, let us assume our material concern is isotropic. So we can say that only two independent elastic constants are involved here in the general spectrum of Hooke's law. We have seen that only two independent elastic constants are existing there. Now, we have seen in stress analysis that at any point there exist three phases of three planes where resulting stresses are only normal or only normal. And there is no shear stress on this particular plane. At any point there exist three such planes, which is the principal plane, which carries only normal stresses and which does not carry any sort of shear stresses. This is our definition of principal stresses. These principal stresses are major or minor or in between. Three stresses is possible. And in between stress can be zero even. These planes over which these principal stresses are the principal planes. Stress is principal stress, strain is principal strain. And the stresses on these planes are principal stresses. So that is clear. There is no shear stresses. A three stress always exists for a particular point. Then on a particular plane, there exists no shear stresses, only the principal stresses. And those also maximum and minimum and zero, maybe zero. And the plane over which are active, they are called as principal plane. Now, at any point we can identify them as small rectangular parallelogram. We make a understood on a point extremely small, infinitesimally small parallelogram or a box whose size is rectangular. Just on a point, its size is rectangular but infinitesimally small, but they are not zero. But we are saying that when this particular box, when the planes of this particular boxes are the principal plane, the basis of this rectangular block after the strain remains rectangular because they are existing, they are experiencing only normal stresses in three directions, maximum, minimum, or zero. They are all straining in normal direction. There is no shear stress. So this is not disturbing this rectangular block remains rectangular. It does not disturbing or takes a parallel shape. The normal speed phase of this box are called again principal axis of strain. So we can choose three normals to the space of this box. They are known defined as principal axis of strain itself. Now, how since an isotropic material, a small rectangle, the faces of which are subject to pure normal stresses will remain rectangle after the deformation. No asymmetrical deformation. So, if there is the principal made with the principal plane, it is not deforming but remains rectangular. It may change its size. Change the size, it can increase or decrease in the size dimension, but not the shape. And normal to this plane coincides with that of principal stress axis. So we are assuming all these faces of this rectangular small size are having faces whose normals are the principal axis, principal strain axis. So in isotropic material, one can definitely relate the principal stresses sigma 1, sigma 2, sigma 3 with three principal strains sigma 1, extra 1, extra 2, etc. There is no gamma or shear stress, there is no shear strain. So we are having from the six equations, we are reducing to six equations with 6 into 6, 36 components. We are using into we are reduced to only three longitudinal stress are reduced only three longitudinal principal strain. So six equations are promptly reduced to three equations. Epsilon 1 is A1, A1 sigma 1 plus eta 2, A2, sigma 2 plus sigma A3, sigma 3 also. So this equation reduced to only three equations instead of six equations. Unknowns are divided to 9 only. instead of 36. Now let the axis XYZ as just I told you, along with the principal stress and principal strain duration. So sigma 1, the if we represent sigma in terms of epsilon, sigma 1 will be A, epsilon 1 plus B, epsilon 2 plus C, epsilon 3, where A, B, C are constant. But we observe that B and C should be equal. Why? Because the effect of sigma 1 in the direction of epsilon 2 and epsilon 3 will be same, which are at right angles to each other, must be same for isotropic material, because for a point they have the same properties everywhere. So due to the effect of sigma 1, epsilon 1, epsilon 2 will be the same. So they have the same constant here because they are same. So for a isotropic material, the sigma 1 equation becomes sigma 1 into A into epsilon 1 plus B into epsilon 2 plus epsilon 3 epsilon x. So if you add 1 minus B minus B epsilon and 1 plus B epsilon here, the equation will become A minus B epsilon 1 plus B into epsilon 1 2 plus 3 by adding a separating B epsilon. But epsilon 1 plus epsilon 2 epsilon 3 in the first variable of the strain, that is J1, or the cubical dilation values and delta. And if we denote lambda by B, A minus B by 2 into B, that is the Poisson's ratio, then the equation will reduce to sigma 1 lambda delta 2 into B into epsilon 1. Similarly, sigma 2 sigma 3 lambda into delta plus 2 into mu into epsilon 1 epsilon 2 lambda delta 2 into epsilon 2 epsilon 3, where delta is known to us because we are supposed to know the strains, and so we can simply have this as known value. We can simply have this as the known value, epsilon 2 epsilon 1 epsilon 2 epsilon 3 are not supposed to be known to me. So we have 3 equations, and we have unknowns is lambda and only lambda and only one lambda. It's the constant lambda mu as Lenz coefficient. This lambda and mu are not. We have to calculate here. We have 2 or 3 equations have 2 unknowns. It's not Poisson's ratio, but it's a Lenz coefficient itself. There are only 2 elastic constants, like Lenz constant involved in the relation between the principal stresses and principal strains for an isotropic material itself. And this can be extended the relation between rectangular stress and strain components also. So out of 36, we are supposed to know 2 elastic constants only, lambda and mu itself. Now, next, let's go to the modulus of rigidity. Let the coordinate axis X, Y, or Z coincides with principal stress axis. Okay. Again, we are following the same model. Principal stress axis is principal plane here, which don't have any shear stress itself. So you have to know, you have to calculate and use the normal tensile stress only, which is maximum or minimum or so. In an isotropic body, the principal strain axis will also be along X, Y, or Z, consider another orthogonal plane. So what we have, x, y, z coordinates is now coordinating with principal stress axis. For isotropic body, strain axis will be also along x, y, and z. For a point, we have this axis itself. Next, another orthogonal plane of reference. Orthogonal means another individual angle is 90 degrees. O dash dash, OY dash, OZ dash, such as the direction cosines of OZ dash and OX and OZ is NX1, NY1, and Z1. Direction cosine means the angle which is separated by OX in from OX dash from OXY OZ by a angle and the cosine of the angle separated by OX from OZ that is given as NX1, NY1, and Z1. And those are Y dash, NX2, NY2, and Z2 that have and OX and Y are supposed to be right angle to each other. Same is the case with the OZ itself. Now, as OX dash and Y dash are right angles to each other, what will happen? NX1, NH2 multiplied by NH2, NY1 multiplied by NY2, and NZ2 multiplied by NZ2 will be equal to 0. As they are all right angles to each other. Just 1 second, please. Let's see that in this one. And which that was are aligned to each other, then NX1. As if we are saying, these two X, Y, are individually perpendicular to each other. So their direction cosines, artificial their own distance cosines will be equal to 0 itself. So what is this? Cos of the angle subtended by OX, OX dash being OX, multiplied by the cos of the angle subtended by OY with OX itself. If we multiply it, it will be equal to 0 itself. The normal stress sigma x dash and the shear x dash tau dash x dash are obtained from Cauchy's formula itself. The resultant stress which we have there only explained because we have the component as like this. Tx dash Py equal to nx1 sigma y, which is nx1 you know the cosine vector means the component of the sigma I multiplied by the cosine vector means what is the is also straight x itself not y only. Just 1 second. X dash vector force on the x axis is multiplied by equal to cosine vector into sigma y, sigma 1, sigma 2, and sigma 3 multiplied with all addition cosine y, multiplication cosine y will give the resultant number of forces along x axis, y axis, and z axis itself. There the components in x, y, z direction itself. The normal stress on the direction explained is obtained, and as the sum of the projection of the components are the normal. As that it will be sigma n square will be nx square into sigma 1 and nx1 ny square into sigma 1 and nj square into sigma 1. Means we have to multiply this component on the x axis with the reaction cosine again. And you have to add it, same, you have to do here, you have to do here, and you multiply it again, you will get this equation, which we have already defined. So sigma x dash becomes sigma stress is normal stress on the x plane. Now we will get with this equation where we know the reaction cosines and we know the principal stress sigma 1, sigma 2, sigma 3 is. Similarly, the shear stress component in this plane, in this plane, x plane, is y direction is obtained as the sum of the projection in y direction, which has reaction cosine nh2, ny2, nj2. So sigma shear stress component does become nh1, ny2, ny1, ny2, nz1, nz2. This h2. At the same time, if epsilon 1, epsilon 2, and epsilon 3 are the principal strain, which is also along xy direction, the normal strain in x dash direction is as normal strain is given by this equation in x square naught ny square epsilon 2 nz square epsilon 3 epsilon. Let's go to the third page. Just 1 second, please. The shear strain gamma x1 is obtained from 36 of the strain analysis. This is given by this big equation 1 by x dash 1 plus y dash 1 and x1, x2, etc. and x1, x2, etc. This is equation 5 and observing that epsilon x1 and epsilon out is comparatively small and uniquely determinated. So gamma xy dash is 2 x1, x1, x2, epsilon 1 plus ny1, ny2, epsilon 2 plus nz1, nz2, epsilon 3, epsilon 2. Substituting the value of sigma 1, sigma 2, and sigma 3 from equation 4 and b, this equation will take this particular form nx1, nx2, gamma lambda to mean epsilon, ny1, ny2, gamma lambda to mean epsilon. If we take the common, if we simplify a bit in terms of the gamma lambda, which will have this equation, and multiply plus 2 into b, we have this equation like this. Hence, from equation 5 to 16, tau hy to the gamma mean gamma x dash y dash itself. This is equation number 8. This equation is this gives the rectangular shear stress components of tau x dash y dash with the rectangular shear strain components of gamma x dash. Comparing these two with relations used in elementary strength of material, one observes that V is the modulus of mobility and is denoted by G itself.